A field-programmable gate array is an integrated circuit designed to be configured by a customer or a designer after manufacturing, hence, field-programmable. The FPGA configuration is generally specified using a hardware description language, similar to that used for an application-specific integrated circuit. FPGAs contain an array of programmable logic blocks, and a hierarchy of reconfigurable interconnects that allow the blocks to be wired together. Like many logic gates that can be interwired in different configurations, logic blocks can be configured to perform complex combinational functions, or merely simple logic gates like an XOR. In most FPGAs, logic blocks also include memory elements, which may be simple flip-flops or more complete blocks of memory. Technical design. Contemporary field-programmable gate arrays have large resources of logic gates and RAM blocks to implement complex digital computations. As FPGA designs employ very fast I/Os and bidirectional data buses, it becomes a challenge to verify correct timing of valid data within setup time and hold time. Floor planning enables resources allocation within FPGAs to meet these time constraints. FPGAs can be used to implement any logical function that an ASIC could perform. The ability to update the functionality after shipping, partial reconfiguration of a portion of the design, and the low non-recurring engineering costs relative to an ASIC design offer advantages for many applications. Some FPGAs have analog features in addition to digital functions. The most common analog feature is programmable slew rate and drive strength on each output pin, allowing the engineer to set slow rates on lightly loaded pins that would otherwise ring or couple unacceptably, and to set stronger, faster rates on heavily loaded pins on high-speed channels that would otherwise run too slowly. Another relatively common analog feature is differential comparators on input pins designed to be connected to differential signaling channels. A few mixed-signal FPGAs have integrated peripheral analog-to-digital converters and digital-to-analog converters with analog signal conditioning blocks, allowing them to operate as a system on a chip. Such devices blur the line between an FPGA, which carries digital ones and zeros on its internal programmable interconnect fabric, and field-programmable analog array, which carries analog values on its internal programmable interconnect fabric. History. The FPGA industry sprouted from programmable read-only memory and programmable logic devices. PROMs and PLDs both had the option of being programmed in batches in a factory or in the field. However, programmable logic was hardwired between logic gates. In the late 1980s, the Naval Surface Warfare Center funded an experiment proposed by Steve Castleman to develop a computer that would implement 600,000 reprogrammable gates. Castleman was successful, and a patent related to the system was issued in 1992. Some of the industry's foundational concepts and technologies for programmable logic arrays, gates, and logic blocks are founded in patents awarded to David W. Page and Love N.R. Peterson in 1985. Altera was founded in 1983 and delivered the industry's first reprogrammable logic device in 1984, the EP300, which featured a quartz window in the package that allowed users to shine an ultraviolet lamp on the die to erase the EEPROM cells that held the device configuration. Xilinx co-founders Ross Freeman and Bernard von der Schmidt invented the first commercially viable field-programmable gate array in 1985, the XC2064. The XC2064 had programmable gates and programmable interconnects between gates, the beginnings of a new technology and market. The XC2064 had 64 configurable logic blocks, with 2 3-input lookup tables. More than 20 years later, Freeman was entered into the National Inventors Hall of Fame for his invention. By 1993, Actel was serving about 18% of the market. By 2010, Altera, Cpl and Xilinx together represented approximately 77% of the FPGA market. The 1990s were an explosive period of time for FPGAs, both in sophistication and the volume of production. In the early 1990s, FPGAs were primarily used in telecommunications and networking. By the end of the decade, FPGAs found their way into consumer, automotive, and industrial applications. Modern developments. A recent trend has been to take the coarse-grained architectural approach a step further by combining the logic blocks and interconnects of traditional FPGAs with embedded microprocessors and related peripherals to form a complete system on a programmable chip. This work mirrors the architecture by Ron Perloff and Hannah Potash of Burroughs Advanced Systems Group, which combined a reconfigurable CPU architecture on a single chip called the SB24. That work was done in 1982. Examples of such hybrid technologies can be found in the Xilinx ZYNQ7000 all-programmable SoC, which includes a 1.0 GHz dual-core ARM Cortex-A9 MP-core processor embedded within the FPGA's logic fabric, or in the Altera Aria vFPGA, which includes an 800 MHz dual-core ARM Cortex-A9 MP-core. The Atmel FPSLIC is another such device, which uses an AVR processor in combination with Atmel's programmable logic architecture. The Microsemi Smart Fusion devices incorporate an ARM Cortex-M3 hard processor core and analog peripherals such as a multi-channel ADC and DAX2. Their flash-based FPGA fabric. In 2010, Xilinx Inc. introduced the first all-programmable system on a chip branded ZYNQ trademark sign-7000 that fused features of an ARM high-end microcontroller with the 28 nanometers FPGA fabric to make it easier for embedded designers to use. The extensible processing platform enables system architects and embedded software developers to apply a combination of serial and parallel processing to their embedded system designs, for which the general trend has been to progressively increasing complexity. The high level of integration helps to reduce power consumption and dissipation, and the reduced parts count versus using an FPGA with a separate CPU chip leads to a lower parts cost, a smaller system, and higher reliability, since most failures in modern electronics occur on PCBs in the connections between chips instead of within the chips themselves. An alternate approach to using hard macroprocessors is to make use of soft processor cores that are implemented within the FPGA logic. NIOS-2, MicroBlaze and Myco32 are examples of popular soft-core processors. As previously mentioned, many modern FPGAs have the ability to be reprogrammed at runtime, and this is leading to the idea of reconfigurable computing or reconfigurable systems, CPUs that reconfigure themselves to suit the task at hand. Additionally, new, non-FPGA architectures are beginning to emerge. Software configurable microprocessors such as the Stretch S5000 adopt a hybrid approach by providing an array of processor cores and FPGA-like programmable cores on the same chip. Companies like Microsoft have started to use FPGA to accelerate high-performance, computationally intensive systems, due to the performance per watt advantage FPGAs deliver. Gates 1982, 8192 Gates, Burroughs Advanced Systems Group, integrated into the S-type 24-bit processor for reprogrammable I/O. 1987, 9000 Gates, Xilinx. 1992, 600,000, Naval Surface Warfare Department. Early 2000s. Millions. Market size 1985. First commercial FPGA. Xilinx XC2064. 1987. $14 million. 1993. Greater than $385 million. 2005. $1.9 billion. 2010 estimates, $2.75 billion. 2013, $5.4 billion. 2020 estimate, $9.8 billion. Design starts 2005, 80,000, 2008, 90,000. FPGA comparisons. Historically, FPGAs have been slower, less energy efficient and generally achieved less functionality than their fixed ASIC counterparts. An older study had shown that designs implemented on FPGAs need on average 40 times as much area, draw 12 times as much dynamic power, and run at one-third the speed of corresponding ASIC implementations. More recently, FPGAs such as the Xilinx VIRTEX7 or the Altera Stratix 5 have come to rival corresponding ASIC and ASSP solutions by providing significantly reduced power, increased speed, lower materials cost, minimal implementation real estate, and increased possibilities for reconfiguration on the fly. Where previously a design may have included 6 to 10 ASICs, the same design can now be achieved using only one FPGA. Advantages of FPGAs include the ability to reprogram in the field to fix bugs, and may include a shorter time to market and lower non-recurring engineering costs. Vendors can also take a middle road by developing their hardware on ordinary FPGAs, but manufacture their final version as an ASIC so that it can no longer be modified after the design has been committed. Xilinx claims that several market and technology dynamics are changing the ASIC FPGA paradigm. Integrated circuit development costs are rising aggressively. ASIC complexity has lengthened development time. R&D resources and headcount are decreasing. Revenue losses for slow time to market are increasing. Financial constraints in a poor economy are driving low-cost technologies. These trends make FPGAs a better alternative than ASICs for a larger number of higher-volume applications than they have been historically used for, to which the company attributes the growing number of FPGA design starts. Some FPGAs have the capability of partial reconfiguration that lets one portion of the device be reprogrammed while other portions continue running. Complex programmable logic devices. The primary differences between Cpl Ds and FPGAs are architectural. A Cpl D has a somewhat restrictive structure consisting of one or more programmable sum of products logic arrays feeding a relatively small number of clocked registers. The result of this is less flexibility, with the advantage of more predictable timing delays and a higher logic-to-interconnect ratio. The FPGA architectures, on the other hand, are dominated by interconnect. This makes them far more flexible but also far more complex to design for. In practice, the distinction between FPGAs and Cpl Ds is often one of size, as FPGAs are usually much larger in terms of resources than Cpl Ds. Typically only FPGAs contain more complex embedded functions such as adders, multipliers, memory, and SerDes. Another common distinction is that Cpl Ds contain embedded flash to store their configuration, while FPGAs usually, but not always, require external non-volatile memory. Security considerations. With respect to security, FPGAs have both advantages and disadvantages as compared to ASICs or secure microprocessors. FPGA's flexibility makes malicious modifications during fabrication a lower risk. Previously, for many FPGAs, the design bit stream was exposed while the FPGA loads it from external memory. All major FPGA vendors now offer a spectrum of security solutions to designers such as Bitstream Encryption and authentication. For example, Altera and Xilinx offer AES encryption for bit streams stored in an external flash memory. FPGAs that store their configuration internally in non-volatile flash memory, such as Microsemi's ProASIC 3 or Lattice's XP2 programmable devices, do not expose the bitstream and do not need encryption. In addition, flash memory for a lookup table provides single event upset protection for space applications. Customers wanting a higher guarantee of tamper resistance can use write-once, anti-fuse FPGAs from vendors such as Microsemi, with its Stratix 10 FPGAs and SoCs. Altera introduced a secured device manager and physically unclonable functions to provide high levels of protection against physical attacks. Applications. Technically speaking, an FPGA can be used to solve any problem which is computable. This is trivially proven by the fact FPGA can be used to implement a soft microprocessor, such as the Xilinx Microblaze or Altera NIOS 2. Their advantage lies in that they are sometimes significantly faster for some applications due to their parallel nature and optimality in terms of the number of gates used for a certain process. Specific applications of FPGAs include digital signal processing, software-defined radio, ASIC prototyping, medical imaging, computer vision, speech recognition, cryptography, bioinformatics, computer hardware emulation, radio astronomy, metal detection and a growing range of other areas. FPGAs originally began as competitors to Cpl Ds and competed in a similar space, that of glue logic for PCBs. As their size, capabilities, and speed increased, they began to take over larger and larger functions to the point where some are now marketed as full systems on chips, particularly with the introduction of dedicated multipliers into FPGA architectures in the late 1990s. Applications which had traditionally been the sole reserve of DSPs began to incorporate FPGAs instead. Another trend on the usage of FPGAs is hardware acceleration, where one can use the FPGA to accelerate certain parts of an algorithm and share part of the computation between the FPGA and a generic processor. Traditionally, FPGAs have been reserved for specific vertical applications where the volume of production is small. For these low-volume applications, the premium that companies pay in hardware costs per unit for a programmable chip is more affordable than the development resources spent on creating an ASIC for a low-volume application. Today, new cost and performance dynamics have broadened the range of viable applications. Common FPGA applications: aerospace and defense avionics, DA-254 communications missiles and munitions secure solutions space, medical electronics, ASIC prototyping, audio connectivity solutions portable electronics radio digital signal processing, automotive high-resolution video image processing vehicle networking and connectivity automotive infotainment, broadcast real-time video engine EduCom encoders displays switches and routers, consumer electronics digital displays digital cameras multifunction printers portable electronics set-top boxes, data center servers security routers switches gateways load balancing, high-performance computing servers supercomputers SIGINT systems high-end radars high-end beamforming systems data mining systems, industrial imaging industrial networking motor control, medical ultrasound CT scanner MRI X-ray PET surgical systems, scientific instruments lock-in amplifiers boxcar averages phase-locked loops, security industrial imaging secure solutions image processing, video and image processing high-resolution video over IP gateway digital displays industrial imaging, wired communications optical transport networks network processing connectivity interfaces, wireless communications baseband connectivity interfaces mobile backhaul radio.